always deeply impressed about how much we already learned about space, about the universe, and about our place in the universe, our solar system. But the next speakers will explain us how we can use computational methods to simulate the universe and actually grow planets. The speakers will be Anna Penzlin. She is a PhD student in computational astrophysics in Tübingen, and Caroline Kimmich. She is physics master student at Heidelberg University. And the talk is entitled Grow Your Own Planet, How Simulations Help Us Understand the Universe. Thank you.
So, hi everyone. It's a cool animation, right? And the really cool thing is that there's actually physics going on there. So this object could really be out there in space, but was created on a computer. So this is how a star is forming, how our solar system could have looked like in the beginning. Thank you for being here and that you're interested in how we make such an animation. Anna and I are researchers in astrophysics, and we're concentrating on how planets form and evolve. She's doing her PhD in Tübingen, I'm doing my master's in Heidelberg. And in this talk, we want to show you a little bit of physics and how we can translate that in such a way that a computer can calculate it. So let's ask a question first. What is the universe? Or what's in the universe? The most part of the universe is something we don't understand yet. It's dark matter and dark energy. And we don't know what it is yet. And that's everything we cannot see in this picture here. What we can see are stars and galaxies. And that's what we want to concentrate on in this talk. But if we can see it, why would we want to watch a computer? Well, everything in astronomy takes a long time. So each of these tiny specks you see here are galaxies, just like ours. This is how the Milky Way looks like. And we're living in this tiny spot here. And as you all know, our Earth takes 1 year to orbit around the Sun. Now think about how long it takes for the Sun to orbit around the center of the galaxy. It's 400 million years. And even the star formation is 10 million years. We cannot wait 10 million years to watch how a star is forming, right? That's why we need computational methods or simulations on a computer to understand these processes. So when we watch to the night sky, what do we see? Of course, we see stars and those beautiful nebulas. They are gas and dust, and all of these images are taken with Hubble Space Telescope. Oh. So there's one image that doesn't belong in there. But it looks very similar, right? This gives us the idea that we can describe the gases in the universe as a fluid. It's really complicated to describe the gas as in every single particle. So we cannot track every single molecule in the gas that moves around. It's way easier to describe it as a fluid, so remember that for later, we will need that. But first, let's have a look how a star forms. A star forms from a giant cloud of dust and gas. Everything moves in that cloud. So eventually, more dense regions occur, and they get even denser. And these clumps can eventually collapse to one star. So this is how a star forms. They collapse due to their own gravity. And in this process, a disk forms, and in this disk, planets can form. So why a disk? As I said, everything moves around in the cloud, so it's likely that the cloud has a little bit of an initial rotation. As it collapses, this rotation gets larger and faster. And now you can think of making a pizza. So when you make a pizza and spin your dough on your finger, you get a flat disk, like a star, like a disk around a star. That's the same process, actually. In this disk, we have dust and gas. From this dust in the disk, the planet can form. But how do we get from tiny little dust particles to a big planet? Well, it somehow has to grow, and grow even further and compact till we have rocks, and even grow further until we reach planets. How does it grow? Well, that dust grows, we know that. At least that's what I observed when I took those images in my flat. Well, so dust can grow and grow even further and compact. But when you take two rocks, we're now in this stage, when you take two rocks and throw them together, you do not expect them to stick, right? You expect them to crash and crack into 1,000 pieces. So we're standing on the proof that planets exist. How does this happen? And it's not quite solved yet in research. So this is a process that is really hard to observe because planets are very, very tiny compared to stars, and even stars are only small dots in the night sky. Also, as I said, planets form in a disk, and it's hard to look inside the disk. So this is why we need computation to understand the process, how planets form, and other astronomical processes. So let's have a look at how we simulate it on a computer.
Okay, so somehow we have seen nature, it's beautiful, and it's just like a tank of water and a bubbly fluid we already have. So now we have this bubbly fluid here in the middle demonstrated, but now we have to teach our computer to deal with the bubbly fluid, and that's way too much single molecules to simulate them, as we already said. So there are two ways to discretize it in a way that we just look at smaller pieces. One is the Lagrangian description, just like taking small bubbles or balls of material that have a fixed mass. They have a certain velocity that varies between each particle, and they have, of course, a momentum because they have a velocity and a mass. And we create a number of those particles and then just see how they move around and how they collide with each other. That would be one way. That was described last year in a very good talk. I can highly recommend to hear this talk if you're interested in this method. However, there's a second way to also describe this, not just going with the flow of the particles, but we are a bit lazy, we just box it. So we create a grid. As you see down here, in this grid you have a certain filling level, a bit of a slope, so what's the trend there, and then we just look for each box, what flows in, what flows out through the surfaces of this box, and then we have a volume or a mass filled within this box. And this is how we discretize what is going on in the disk. And actually, since we are usually in the system of a disk, we do not do it in this nice box way like this, but we use boxes like those because they are already almost like a disk. And we just keep exactly the same boxes all the time, and then just measure what goes through the surface in these boxes. So this is how these two methods look like if you compute with both of them. So one was done by me. I'm usually using this boxing method, and the other was done by my colleague. You see these, like, when you look at them, at the colors, at the structure, here you have the slope inwards, you have the same slope inwards here, you have even this hilly structure here, the same here, but what you notice is you have these enlarged dots that are these are really the mass particles we saw before, these bubbles, and here you have this inner cutout. This is because when you create this grid, you have a very region at the inner part of the disk where the boxes become tinier and tinier, and, well, we can't compute that. So we have to cut out at some point the inner part. So here, when you go to low densities, these bubbles blow up and distribute their mass over a larger area, so it's not very accurate for these areas. And here we have the problem, we can't calculate the inner area. So both methods have their pros and cons and are valid. But now for most we will focus on this one, just so we have this nice actually stream features. So again, going back to the boxes, we have to measure the flow between the boxes. This flow in physics, we call it flux. And we have a density, rho 1, a density, rho 2. And the flux is the description of what mass moves through the surface here from one box to the next. So if we write this in math terms, it looks like this. This says the time derivative of the density, meaning the change in the change over time. So how much faster or slower you go, that velocity would be a change in time. And then this weird triangle symbol, it's called nabla, is a positional derivative. So it's like a slope. So how do we change our position, actually? So if we look at the density over time, it should correlate to what inflow we have over position. That is what that says. So, and then we have in physics a few principles that we have always to obey because it's just almost common sense. One of them is, well, if we have mass in a box, well, like this, the mass should not go anywhere unless someone takes it out. So if we have a closed box and mass in that box, nothing should disappear magically. We should stay. It should all stay in this box. So even if these particles jump around in our box with a certain velocity, it's the same number of particles in the end. That's, again, the same equation, just told in math. So a second very rudimentary principle is if we have energy in a completely closed box, so for example, these nice chemicals here, and we have a certain temperature, so in this case our temperature is low, maybe like outside around 0 degrees Celsius, and then we have these nice chemicals down here, and at some point they react very heavily. We suddenly end up with much less chemical energy and a lot more thermal energy. But overall, the complete energy summed up here, like the thermal and the chemical energy, also the energy of the movement and the energy of potential added up to this variable u, that should not change over time if you sum up everything, because our energy is conserved within our closed box. And then the third thing is, I think you all know this, if you have like a small mass with a certain velocity, a very high velocity in this case, and it bumps into someone very large. What happens? Well, you get a very small velocity in this large body, and the smaller mass stops. And the principle here is that momentum is conserved, meaning that the velocity times the mass of one object is the same as then later for the other one, but since it's larger, this product has to be the same. That doesn't change. And we have also to, like in our simulations, to obey these rules. And we have to code that in so that we have physics in them. So you say, okay, this is really simple, these rules, right? But actually, well, it's not quite as simple. So this is the Navier-Stokes equation. It's a very complicated equation. It's not completely solved. And we have here all that is marked red are derivatives. Here we have our conservation law. That was the nice and simple